This persistent issue of food desert primarily stems from the absence of a full-service grocery store and transportation. Individuals residing in the food desert area frequently face the challenge of having to travel significant distance to obtain the essential grocery. So this leads to increasing the transportation expense and further strain already tight household budgets. Consequently, this is a growing interest in exploring the solution to improve the food access in this region and alleviate these adverse health consequences associated with the food desert. One proposed strategy is the placement of a public transit route and a stop near the grocery stop in the food desert area. This approach focuses on the synergy between the transit system and food distribution system, providing the reliable and convenient cross to healthy food option for low-income residents who might rely on transit as their primary mode of transportation. Recent effort in cities like Philadelphia, Atlanta has aimed to enhance the access to stores that stock nutrition the food. This initiative has demonstrated expanding the availability of a transit option, whether in terms of geography, convergence, or frequency, may improve their food access level. As community engagement efforts benefit transit-dependent individuals by enhancing their access to food supply. However, it is still essential to recognize that not all the low-income residents in food desert area rely solely on public transit. Furthermore, public transit routes in rural food desert area typically have a limit of a vehicle availability and the low frequency, making effort to increase the food access somewhat cumbersome due to the challenging of balancing the responsiveness and also efficiency. To tackle this challenging, we trying to make the emergence of automated vehicle technology has provided a solution to the food delivery. So the core research hypothesis is that the substantial cost saving and social economic benefit can be achieved at a systematic level by implementing an innovative food delivery approach that effectively coordinate the operation of conventional vehicles like ground transportation, like trucks, buses, and vans, and small autonomous robots such as drones and any wheeled mobile robots, which is widely can be seen in the Atlanta and those large cities. So the primary objective of this research is to improve the food access by introducing a hybrid optimization methodology is integrate the integer programming and machine learning. So this methodology is designed to facilitate the cooperative schedule and the routing for traditional vehicle, ground transportation, and the autonomous robots, ultimately enhancing the full accessibility in the food desert area. Both the traditional vehicles and autonomous robots like drones are employed in a cooperative capacity, each differing in terms of the operational environment, speed, size, maximum payload capacity, and operating costs. By assembling a fleet of the conventional vehicles and a core of drones, whether their coordination is physical or visual, systematic benefit, including the heightened adaptability and versatility, and enhanced energy efficiency can be potentially unlocked. Within the vehicle and the drone cooperation scheme, it is important to note that the multiple robots each tasked with a delivery full item to distinct destination can originally into a cooperative groups, yielding the collective advantage. Individual UAV can dynamically join or depart for such groups as the operational needs. Given the limitation in terms of weight and size of the drone, especially when carrying the large payroll over extending period. They can strategically piggyback or can be mounted into the conventional vehicle with a greater load capacity but less maneuverability. The drone can be launched from the truck, complete the customer's delivery, and subsequently dock at a designated position to rejoin the truck once their delivery are concluded. Concurrently, the truck can also continue serving additional customers along its primary route, later get together with the drones at a prearranged location. In between delivery, the drone have the option to ride on the truck for refueling or recharging purpose. Another thing I want to mention that we also work closely with the agency, university, and industry partner to turn actively the research problem into the course projects. So students are just not only like solving hypothetical problems, they are working on the issue that transit agency are actually dealing with occasionally. So one thing I care a lot is closing the loop. For example, the research-informed teaching train students, and students go on to help solve the same problem we are studying. So we have some poster competition where students can present their work. And we also have the visuality section development that learn how to do it, and futures where the transportation suddenly become the real when you're standing next to it instead of modeling me. So for me, education and outreach are not just ads-on, they are on how we make sure our research doesn't just stay in papers, but also actually move people, sometimes literally. So these are some of the visuality drone use we developed due to the Florida state. We have a very strict use regulation on the drone use. Quite a few places are not able to procure the drone for students for doing the survey. So we trying to build this visuality lab for students that can make use of the UAV drone for like doing their survey work, normally usually conducted in the lab. And these are the procedures of how we develop this tool in terms of the drone, how. So those needs quite a few research hours on this. And we also develop a visuality lab for doing the survey using the drone and also using other equipment. This is the lab. We provide immersed city area environment, assuming students bringing the equipment, doing the survey on the site, and we might also including using the drone for flying, doing the research. So more about the research. Let me delve deep into the specifically what this research topic about. We introduced to the delivery mode. One is the truck only delivery, which is common in the deliver. So the neighbor will drive the truck and deliver the package in each customer point. Another one mode is called the drone UAV assist truck for delivery. So this delivery mode is considered the most efficient drone delivery mode because it combines the strengths of both truck and drone. Drone can assist with the last mile delivery, which is the most expensive and time-consuming part of the delivery process. By using the UAV to carry out the final step of the delivery, those companies can save time and money and while providing their customer with a faster and more convenient service. However, truck only remain the dominate delivery method in various delivery systems because of their large capacity and ability to cover long distance. By incorporating the drone into the delivery process, we obtain a faster and a more cost-effective last mile delivery mode. Because most of the logistic companies have used these two modes in their delivery system, however, they haven't like dynamically used their according to different demand density in the service area. The key question addressed in this research paper is investigate when to switch when between the truck-only delivery and Joom Assist truck delivery, which provide a delivery system with a maximum benefits. There are very few fundamental model or methods available to make a switching between these two modes. In this study, we explore like 3 modes to switch between two different delivery modes. So in this research, we also have a major 4 contribution. First, we developed the cost function for those delivery mode, which establishing with the continuous approximation model through the simulation of the demand density with the geometric Brownian motion process, because we consider the future demand, which is uncertain and dynamic, and we may use of the real option approach to simulate the future uncertainty of the demand. We develop a myopic policy and the deterministic policy by determining to consider the demand density as an uncertainty factors, then use the market entry as a real option approach, which is approach originally from the financial area. We extend this approach into our background story. We extended these 2 models to stochastic dynamic model to find the optimal switching timing between those 2 transportation delivery modes. So these 2 delivery modes are shown in the figure. In the truck-only delivery, we have the conventional truck reach the service zone after leaving the depot point and proceed to the delivery area next. We use the blue bone line to represent the truck route. So the last delivery step is carried by the human driver, and it takes as long as necessary to load and unload items, find the parking space, parking cars, and performing delivery activity. During a 6-truck delivery is that the truck and then multiple Joom will work together to finish the final delivery step. The truck complete the long-distance transportation from the depot, and it release multiple Jooms as getting closer to the delivery point. These Jooms are responsible for making one delivery each represent using the black dot line. During the delivery travel, the truck doesn't need to wait for the Jooms. With the continuous approximation model, we have 2 assumptions. One is the delivery zone as a model as a compact region and convert by the swaths of a width approximately across the continuous approximation model, which is originally from the D'Agostino 1984. Secondly, the delivery density is distributed randomly and independently in the service region. The last mile travel for truck and Joom are shown in a figure, which is an example of a 3 Joom may launch in the truck, and truck serve the delivery point, represent the.
Actually have photos up here. There were 6 tiles installed at a detour bridge up in Ontario, Canada. They had to do some work to the bridge structure, so they installed one of the end vents for the UAPC piles. The first
Sorry, maybe someone forgot to mute his mic. So the truck serve the delivery point represented by the black square, and Joom serving the delivery point represented by the red car. So let's look at the cost function. We have the cost function that's showing the total cost per customer or per delivery point, including the operation per units of distance. And we have the stop costs per the delivery point, operation costs, including the management, maintenance, and also operating the vehicles, that depending on the delivery distance. And the total travel distance of a truck delivery will including the line haul distance between the depot and also delivery area and the tour distance to each customer in the delivery area. So the start cost is the time values of delivery staff and the Joom usage cost. Through this equation, we can get the cost per delivery points or customers. Because we require calculating the delivery cost of the entire service area, we need the average cost per delivery points multiplied by the service zone size and the demand density. In addition, we can calculate the overall cost of June 6 truck delivery by the similar equation. So these are the based on the two cost functions, since we're trying to compare those two delivery mode. By compare these two cost functions, we can construct a cost saving function when got the difference between them. And we model the relationship between the cost difference of delivery system and demand density of the service zone through the baseline value. When cost saving is greater than that, means the used truck only will need greater cost compared with the Junior 6 truck mode. According to our result, truck only delivery is better than Junior 6 truck delivery when demand is relatively low, because the total cost of a Junior 6 truck delivery is higher than that of a truck only delivery. Otherwise, it will be waste to introduce the drone at a low demand density, because we introducing then it require additional operating and procurement cost. So our research different from the static model because we examine the delivery fleet's switching problems under the future demand uncertainty. Based on the historical data showing our future demand for the needs, it's uncertain. It could be due to specific events. It could be due to the adverse weather. It could be due to the disaster happening. That result in the demand could be very uncertain and fluctuated. To model the changing of future demand, we leverage the geometric Brownian motion, which is a method to simulate the dynamic time-sensitive nature of uncertainty. Let me introduce the two switching model. Firstly, the myopic switching model is characterized by the operational switching action as the saving cost is zero. Whenever the initial save cost between the two delivery services more than zero, the system automatically switches to the service with the lower cost. You can see at the figure. During the initial planning phase, the truck only delivery is the better service due to its low cost. However, when the cost of a June 6 truck delivery drop below that of truck only delivery, then a switch will occur. So in the deterministic switching model, switching occurs when the cost saving between the two services surpass the switching cost threshold. If the switching cost is considered whenever a service switch request, the decision to switch the delivery service is based on whether the initial save cost between the two modes is the switching cost. By using the entry access real option approach, we extend the deterministic dynamic problems to the stochastic dynamic problem to find the optimal switching timing between these two delivery modes. Market entry access real option is a decision-making tool that's particularly useful in analyzing the switching problem in a dynamic and uncertain environment. So historically, there's the first research using such methods into the transportation field is the one published in the Financial Economic 2008 that they modeling the future, the freight price, which is a dynamic. They make use of such methods to help the owner of the ship to determine when to ship the dry bus, when to switch to the wet bus. Instead of finding the single chargeable one is better than the other, they use the measures of market NGS real option. They found that the switching point could be our hysteresis impact, like they will have an upper and a lower chargeable. That it might not necessarily switch at the middle points. Whenever it crosses the higher threshold, it will switch. For example, here is a dry bus. When it hit the lower bump, it will switch to the web bus operation. So we also make use of the similar methodology applied to our delivery. So the problem of stochastic switching between the delivery mode can be addressed using the access equilibrium pricing. So we view like one kind of delivery mode as a kind of access. We quantify that use the differential equation using the dynamic equilibrium value switching based on the stochastic process. Specifically, we establish this access equilibrium pricing equation for the equilibrium value of using truck only and Zhong assist truck delivery based on the shuttle between the two modes. So we are able, by applying the eta llama, we are able to obtain the upper level and also the lower level for switching point. And for some special case where the switching cost becomes zero, the upper and lower threshold will converge, become a single threshold. With those above three equations, we can obtain a nonlinear equation. Through solving this nonlinear equation, we are able to calculate the optimal switching timing without the switching cost. So one simulation round of demand density can be shown in the figure at the top, that along with the criteria of stochastic switching without cost, there's only one single threshold where the switching cost is zero. Whenever the demand is this 65 around threshold, the delivery system will switch from, for example, truck only to Zhong assist truck. When the demand density drops below that, the system will switch back to the truck only. And when the system needs to consider the switching cost, we can get two thresholds based on the stochastic switching model. The ideal thresholds are upper and lower bounds. According to this model, switching timing will be delayed because switching costs need to be considered. They will create the hysteresis effects. Therefore, our switching points are much less relative to a stochastic model that does not consider the switching cost, which can be shown in the second. So the performance of different switching mode is calculated in the table. The cost saving by our proposed model, that is a Zhong assist truck, can increasingly significant compared with the deterministic model, which can improve by 43% in the same planning horizon using the same trajectory of a future estimation of the demand. So we also apply the multiple option. We design like scenario with some multiple policy options rather than just two, making it particularly useful for a large region with a multiple service room. So this model allows for a gradual transition in response to different demand density rather than a abrupt shift from like a full area of a truck only fleets to a complete Zhong assist truck fleets. Initially, the truck only, the Zhong assist truck fleet operation can be introduced in a higher demand, while the truck only service remain in a lower demand region. As demand grows, the transaction expand incrementally and eventually leading to a full area of Zhong assist truck deployment. So with a multiple Zhong assist truck, it could be increasing from the numbers of two Zhongs mounted with a one truck until to 10 Zhong mounted to one truck. So this phase adaptation optimize resource allocation and avoid the high operating costs associated with the immediate switch to the full area Zhong assist truck fleet across the whole region. Under the static analysis, the scenario with the lowest cost change depending on the demand density. For lower density, which is below 58, and the truck only has the lowest cost, when demand density is increasing, then a hybrid mode like multiple Zhong, maybe number of Zhong will be more mounted with the truck, will become a more optimal choice just based on the cost for demand density. So in the multiple region switching model, the switching process is divided into two stages. First stage, which is just switching from the truck only to the hybrid mode. The second stage will be from the hybrid mode to the Jones 6 truck. Therefore, there are two switching thresholds for switching up and down for each of the two stages. As the demand increase and reach to the upper threshold of stage one, we switch from truck only to hybrid mode. And then the demand continue to increase and reaches to the upper threshold for stage two. We continue to switch from the hybrid mode to the Jones truck mode. And then the demand will fall back to the lower threshold of the stage one. We first switch from the Jones 6 truck back to the hybrid mode. And if it's continue to fall back to the lower threshold of stage two, we will switch from hybrid mode to the Jones only mode. So we not only study the modeling, like the mathematical proposition, but we also interested in deploying our model to the practical area. So we select the Miami-Dade County as the piloting place with the base year of the dynamic switching model set in 2021. According to the sensor data, approximately around 2.6 million individual residents within the Miami-Dade County area. 65 package delivery are generated every person in the year 2021 in the U.S. Utilizing the sensor data, we found that the landing area of Miami-Dade County is about 2,431 square miles. Consequently, the average population density is 1,000 persons per square mile. Therefore, we estimate the average daily delivery demand in the Miami-Dade County amount like 195 package per square mile. And there are three logistic operators, the USPS, UPS, and the FedEx dominate the parcel delivery industry in the U.S. The combined parcel volume handled by three companies could nearly 80% of the U.S. parcel delivery in 2021, based on the literature. The table provides the daily demand density from three companies, determined based on their respective market shares. The demand growth rate and the volatility rate for these companies has been determined using the performance data sourced from the Picnic Browse report from the literature. So this table, it shows the demonstrate that both the deterministic and stochastic model lead to the greater the safe cost compared with Miami switching policy. Important significantly, the stochastic switching model can offer a more realistic decision-making process by considering the uncertainty of demand through the upper and the lower threshold. Additionally, the figure outlines the time period for determining the optimal delivery service for various logistic operators. It illustrates the optimal delivery plan. The result of the case study indicated that our proposed dynamic switching model can enhance the switching benefits for the logistics operator. So based on the population data, it can be found that demand is extremely unbalanced within the region. To validate the benefits of our dynamic policy, we select a 3-day with a varying demand density based on the average demand density across the entire Miami-Dade County. In the static policy shown in the figure A, that is the entire region is serving only by the truck-only fleet, regardless of the demand density variation. In contrast, Figure B represents that delivery can be handled by 10 drones mounted to the truck fleet with varying the fleet configuration. For example, every 2 drones mounted with 1 truck, or 5 drones, or even 10 drones. And Figure C is showing the dynamic policy where we adapt like the fleet deployment to the varying demand density within the region. Under this policy, the truck-only fleet is strategically deployed to area with the lowest demand. And Zhong 6 truck fleets with like a 2, 5, 10 Zhongs are allocated to the zone based on the respectively demand level. Additionally, this figure, the table showing the cost comparison for different policy across these Miami-Dade County region demonstrate that the alignment policy consistent result in a lower cost. So these are the conclusion. So we have found that truck-only delivery, which is preferable when the demand is low. The numbers of switching points could be reduced if the switching cost increase. When it is switching like one mode to the other mode, it will involve cost. The switching points will become less. It will be also delayed because of the needs to satisfy the benefits by each switching point. It's greater than the switching cost. And drawing from the market entry asset real option, stochastic model is proposed to find the optimal switching timing. We found that this model can result in 43% reduction in the cost compared with the myopic policy over the 1 year of similar demand density. Our model has demonstrated in Miami-Dade County area with the data represent the three major logistic operators like UPS, USPS, FedEx. Then we also found that our proposed switching model can greatly help them to reduce the cost. So this case study indicate a simulation outline the delivery service plan for each of the logistic operator. In the future, so as you might see, the geometric Brownian motion can be extended to like a mean reverting process, which is more suitable for the transportation because when our demand, we fluctuate, simulate the future uncertainty, but finally it will convert to the mean value. So maybe the mean reverting process may be more suitable. We could consider demand, also consider the demand in the future could be like jump significantly or drop significantly due to some incident happen, unexpected event like COVID-19. Those kind of event result in people buying grocery from the Amazon, from their online shopping may be less significantly reduced. So demand density can be expressed within the, those jump integrated into those geometric Brownian motions to quantify how for those logistic company to better planning integrate with this June for delivery. To optimize our system cost effectively, we recognize the needs to tailor the optimal numbers of a mounted June to match those varying demand density. As you can see shown in the figure, region with a low density may need fewer drones per truck, where more drones can mounted to truck could be allocated in the high density area. We can even consider the congestion effect, but here we have not considered that due to the limitation of a continuous approximation model. But we can also make use of based on the network model to quantify network congestion level to see how whether June assist track can help to release the traffic congestion and also environmental impact. In our forthcoming research, we hope to jointly determine the optimal switching timing and varying zone number, like the zone capacity with the density of the characteristic unique to each region, analyzing the shifts in benefits corresponding to numbers of the zone in it is the future research direction. To support all of this work, I'm fortunate to have my research lab, those students helping me to work on that. We are a very diverse team of a scholar represent a range of different academic background and cultural perspective. Yeah, so each person on this team bring a significant, a unique contribution. I want to recognize their hard work and dedication on the research. So thank you so much for your listening. This is my contact information. If you have any question or would like to continue the discussion and any opportunity we can work together to collaborate, please feel free to reach out. Thanks.
Thank you, Qianwen. Wonderful presentation. Due to my oversight, so many students were not able to listen to join at the first beginning minutes. So I'm wondering if you can give them more information regarding the background and context of the problem, like why are we looking at the switching problem, and why do we consider and the uncertainties in demand, so they can have a better idea about the whole context. Thank you.
Yes, I appreciate the questions. Our hypothesis is that traditionally we make use of the truck for delivery. So the truck have to go through as you can see, service area. The truck have to go through every of the customer points, and there's a last mile delivery cost could result very expensive. But instead of using truck only, we can make use of the drone for last mile delivery. For example, the truck may only serving as the major arterial, and then the drone might fly into the communities to save the time and also the energy and also the fuel cost of the truck. And whenever the truck are flying in the major arterial, the drone will flying at the same time to multiple delivery points. And then when the truck moving to the next customer, and the drone will flying back and mount it on the truck and to rejoin and study to deliver to the last point. Based on our model, we found that because truck only and drone, a 6 truck for delivery, they have a significant difference in the cost. We found that when demand is low, it's good to use the truck only. But due to the demand become higher, become the dynamic, and it is better to make use of the drone assist truck. Just based on our static model, we found that when just from the static model, when we assuming the demand is static growing, that drone assist truck can save quite a few of costs. So this model trying to propose a dynamic switching the policy that whenever the demand is changing due to the uncertainty, the numbers of a drone can be mounted to the truck, or it could be multiple drone mounted to the truck for delivery.
Okay, thank you. So if you have questions, feel free to unmute yourself, or you can type your question in the chat box. So Qianwen, I'm wondering for like a typical scenario when a truck driver needs to deliver the packages on a certain day. So that would mean like the truck has a knowing number of loaded packages, right?
Yes.
So can you explain like where does the uncertainty come from? Is it like over time from a strategic perspective of the company, or it may result from other sources?
Yeah, that's a great question. The uncertainty we quantify is from the demand side. As you can see here, the needs for the delivery. So we did not work on the supply side, the logistic company there uncertainty operating side uncertainty. We only quantify it could be due to the reason of a COVID or due to the season weather become cold. People have or it could be just because of the holiday. People have needs for buying the online things that result in the demand side could be like uncertain. So we just also like make use of their UPS, USPS, FedEx, their data showing like every month and also every day their delivery, the package could be like make using of these geometric Brownian motion to calibrate those parameters.
Yeah, thank you for clarifying that. I'm also wondering, do you see any potential of this like hybrid delivery mode during disaster or adverse weather we are having now in many other states? I feel like maybe sometimes it's not only about saving cost or time or improve time efficiency. So in some certain like adverse weather conditions, maybe drones, they would have the unique advantage to deliver the goods. That might be the only option. So do you agree with that? And if so, can you explain how we can use your framework to approach the problem?
Yes, that would be definitely like great idea to extend this work because consider in a disaster scenario, some of the road and lane was flooded or become invalid. That's the delivery might like humanity, those items might not able to deliver by the truck. This time, so at this stage, we might make use of the drone. How we can use the drone money on the truck for helping people for deliver the vaccine, for example, to deliver the water purified tap, those things. So it will play a significant impact. I do believe there is a potential to work on that. In particular, consider the disaster scenario that's people locate at different disaster-prone area. They might not able to leave. They do need some essential goods with the drone. We can also quantify this, like since people who live in the region, that's their needs might be also like using the uncertainty like a jump diffusion process. That's kind of adding the volatilities to the demand side and how to assume this can be like extended. For example, currently we only consider a continuous approximation model, consider the average distance of a travel in a general rectangle region or the general area, but this work can be extended to the network base. So when it is a disaster scenario, some of the road and link become inaccessible, and how to make use of the drone flying instead of using the truck dropping those items nearby.
Yeah, so maybe we can transfer the accessibility problem to distance. Like if this location is not reachable or accessible by the truck, maybe the distance to that location is infinity. So
yes,
then under this framework, maybe we can see what will happen. Maybe if the benefits of drone will be more amplified, or we can see the great potential of this hybrid mode.
yes. In the disaster, the framework, it could be adjust the objective function, might not necessarily, which is different from this one. This one is from the economics perspective. In a disaster scenario, we might just consider the unmet demand, trying to minimize the unmet demand flying the drone.
Yes, that'll be great. Okay, Marvin, you can unmute yourself and answer this question. ask a question.
Okay, thank you, Dr. Vivian. I just have a couple of questions. First of all, I want to know the software you use to develop the virtual reality drone game. And
Yes.
The second one, I wanted to know the safety concerns with the drone delivery, because on November 18th, Fox News reported that Amazon's drone hit an internet cable, which was like an invisible structure. So how are research being done to ensure that these problems do not happen during drone deliveries? Thank you.
Yeah, that's a great question. First of all, the drone visual reality system we developed, we use the Unity. Unity is open source for free, so everyone can make use of the resource through the Unity system. So my student just make use of this tool to develop this platform. And similarly with the drone, also the same. The second question, I wish I could answer that. Yes, we do find there's quite a lot of a safety concern. Due to the safety concern, like FDOT and also most of the public institute, they require you to have the license, flying license for the drone UAV before you, and also get the approval. That is a very quite straightforward to have that. So that's why the reason we need these visuality for helping students maybe pre-training, or like we can also propose to FDOT, like a workforce development, like how to help people to make use of emerging technology such as the drone. Those are UAV. They have to receive the essential training, have the essential background knowledge on the how to make using of it, and the concern of their safety. I think that will have some great potential to propose to those agencies to get such support.
All right, thank you.
Vivian, we have a question in the chat. The question is, do we know the maximum weights the drones can take, and how does that affect the deliveries?
Yes, that's a great question. So in this research paper, we do not really consider the weight that the package of the package. But we do have currently working on a paper right now under review of the part B, is like we do consider the green drone delivery problems. That when you're using the drone for delivery, you might carry multiple package. Some are heavy, maybe like 5 pounds, 10 pounds. Some are maybe relatively light, just 1 or 2 pounds. How we can deliver these package, how to assign them for each chip could be a significant problems. Because we found that if to straightforward, we might have an intuitive sense that we would rather to carry maximums of the weight of the one drone. For example, it can carry maybe at most like 30 pounds of a package. We're trying to make full use of it and then deliver like one by one based on the routing. So this is our intuitive, like this may be most cost-effective version one we can apply. But in reality, we do some calculation. We do find that it might not necessarily the most safe energy one. We found that sometimes it may be even like saving the energy. You might just only deliver twice or 3 times, multiple times, instead of whether we should deliver the first is a most heavy one, or the second maybe less weight one. There's a combination out there. So we do have a running green drone delivery problems. Consider the package of the weight and the trips it travels, and see which what kinds of the delivery mode could be like a sustainable and safe energy. This is also a very interesting problem, and we are still currently the paper is under review.
Great, thank you. We look forward to that. Maybe you can give us another presentation for that.
Yeah.
Okay, I think it's already 1 p.m. So thank you again for a nice presentation. And thank you guys for joining us. We look forward to see you next time. Thank you.
Yeah, thank you.